Good morning. Today I am going to explain you the derivation of the expression for electric field intensity at any point on the axis of a circular charged ring. So, consider a charged ring. This is a charged ring, circular ring of radius r. This is the axis of the ring. Let P be a point on its axis at a distance x from it. See, the ring is perpendicular to the plane of the board. That is why we have represented like this. Okay. So, axis is like this. So, this is the axis of the ring. P is a point on its axis. Our intention is to find electric field intensity at any point on the axis of that circular charged ring. Now, let Q be the charge given to the ring, R is the radius. Let us consider a small element with a charge dq. Electric field intensity at the point P due to this element, it will be in this direction. Let this be dE. If this is theta, this is also equal to theta. Its component along x axis is dE cos theta, along y axis is dE sin theta, and it has an identical component here also. If you draw electric field intensity due to this, its component is also along this direction dE cos theta, other component dE sin theta will be in this direction. So, these two just get cancelled, only these two components they add up. Keeping this in mind, we can say the net electric field intensity at that point is equal to integral dE cos theta. Now, what is dE here? This is the electric field intensity created at this point due to this charge. So, 1 by 4 pi epsilon naught into dq by the square of this distance. From Pythagoras theorem, this distance is square root of r square plus x square. Square of that distance becomes r square plus x square. Substitute this in the equation 1 and we see what happens. dE is equal to, E is equal to integral dE cos theta. So, integral dE is 1 by 4 pi epsilon naught dq by r square plus x square cos theta. From this diagram, cos theta is adjacent side by hypotenuse. Adjacent side is x, hypotenuse is root of r square plus x square. So, cos theta is x by root of r square plus x square. So, we can take all the constant factors outside. It is 1 by 4 pi epsilon naught x by r square plus x square to the power of 1 plus half, that is 3 by 2 integral dq. Integral dq is nothing but the total charge on the ring. So, electric field intensity at any point on the axis of a circular ring is 1 by 4 pi epsilon naught q into x by r square plus x square to the power of 3 by 2. This you have to memorize. Okay. In the competitive examinations, you do not find this time to solve the entire thing. So, electric field intensity at any point on the axis of a circular ring is 1 by 4 pi epsilon naught qx by r square plus x square to the power of 3 by 2. Now, in this I am asking you two questions. At the center. At the center means x is equal to 0. If x is equal to 0, E is equal to 0. at the center of the charged ring, electric field intensity is equal to 0. If it is a small ring and x is large, r is negligibly small when compared to x. What happens? This r is neglected here. So, it becomes E is equal to 1 by 4 pi epsilon naught q x by x square to the power of 3 by 2 is x cube. It's an interesting finding, isn't it? 1 by 4 pi epsilon naught q by x square, where x is the distance of the point from the center of the circular ring. So, if the ring is too small compared to the distance, the ring acts like a point charge. Due to a point charge at a distance x, electric field intensity is nothing but 1 by 4 pi epsilon naught q by x square. So, here at any point on the axis of a circular ring, electric field intensity is 1 by 4 pi epsilon naught q x by r square plus x square to the power of 3 by 2. At the center, 0. At a long distance of a small ring on the axis, 1 by 4 pi epsilon naught q by x square, the ring just behaves like a point charge. Okay. So, that is E at any point on the axis of a circular ring. Now, we are going to consider an expression for electric field intensity at the center of a circular arc of linear charge density lambda. So, we want to find out an expression for electric field intensity at the center of a circular arc of linear charge density lambda. Linear charge density means the total charge by total length of the ring is called linear charge density. Here we are considering a circular arc. Let this be an arc making some angle. Here this is the center of the arc. Let the charge given to the arc is positive and linear charge density is lambda. Now, let r be the radius of the arc. Our aim is to find electric field intensity at the center. Okay. Now, just this is the horizontal line, this is the vertical line drawn there at the center. Now, to find electric field intensity at the center due to the entire arc, let us consider a small element making an angle d theta here. Okay, this is a small element making an angle d theta here. The length of that element will be r d theta. Let theta be the angle made by that element with this line, right? So, what is the charge on that element? Charge is equal to linear charge density into length of the element, lambda into r d theta. What is the expression for electric field intensity created by that element at the center? So, it will be along this direction because it is positive. So, electric field intensity will be away. So, dA is equal to 1 by 4 pi epsilon naught dq, that is lambda r d theta by r square. 1 by 4 pi epsilon naught dq by r square. Now, let us, if this is E, if this is theta, this is also theta, its component along this direction is dE cos theta and its component along this direction is dE sin theta. Now, you can consider if there is one element here exactly at the same angle, there will be another element creating an exactly the same electric field in this direction. So, this component becomes dE sin theta, and this component becomes dE cos theta. If you observe, those two components get cancelled and these components, they get added up. So, the net electric field intensity created at the center is d integral dE cos theta. So, here 1 by 4 pi epsilon naught, just I am taking all the constants outside, lambda by r integral cos theta d theta. Here limits, suppose actually here this angle is theta, the other angle will be minus theta. So, minus theta to theta. See how you are getting that minus theta to theta, I am writing it here. So, this angle, say minus theta, we are starting from this point and this is making an angle theta. So, minus theta to theta. So, 1 by 4 pi epsilon naught lambda by r cos theta integral is sin theta. So, limits are minus theta to theta. If you substitute the limits, let us see what do we get here. This is equal to 1 by 4 pi epsilon naught lambda by r sin theta minus of minus sin theta. So, this is 1 by 4 pi epsilon naught lambda by r 2 sin theta. That is the expression for electric field intensity at the center of an arc, charged arc, making an angle 2 theta at the center. So, it is lambda by 4 pi epsilon naught r into 2 sin theta, or simply we can say lambda by 2 pi epsilon naught r into sin theta, where theta is this angle. Okay. So, I will stop there for today. I will continue in the next class with some more topics. Thank you and bye-bye.